right? So Reynolds number is a non-dimension or dimensionless variable. It means that it has no units. So how we can assign the symbol for this Reynolds number? R E. This is the standard notation for this dimensionless variable. And sometimes this variables is given a subscript to differentiate its application, right? For example, if I say that Reynolds number, then I have D as a subscript, where D can be diameters, right? And so on. Depends lah, right? Uh, how we want to indicate D, right? Maybe D can be used as diameter. It can also say that Reynolds number L. So L can be laminar flow, or RE can be called T to represent turbulent flow to differentiate, right? So we have various type of flow. So these two represent nature of fluid flow. And as I said, it's been used for specific purposes. So this is the actual physical situation. So we have a pipe flow. This is a pipe wall, right? So if I just take a cross section there, right? So this is a pipe wall, right? Let's see, I just cut it here. AA, right? This one is section A, right? And let's say this one is section B. So this is what we see. This one is B, right? This is what we view for this case. And the actual flow inside here, because of there is a friction, the velocity profile is 0 at the wall, right? This for laminar flow. So we have a parabolic velocity distribution, right? This is the center line. So at that position, this is the velocity vectors, and this is the fluid particle that move with a certain speed, right? V, and this varies with R, right? Because this is the coordinate system that we use. This one is X. And in order for us to evaluate the mass flow rate, for example, as we given in the lectures, we have m dot equal to integration density time the velocity time 2 pi r dr, right? So this is the definition that we use to evaluate the mass flow rate. But in most of the fluid mechanic course, we don't use this equation, but this one is specific for detail for a problem that that requires you uh, to determine the velocity distribution. Maybe we would like to find the friction, right? So then we need the actual velocity distribution. Okay, so that will be the now. But during our course, we mostly assume, right, this velocity distribution uh, is approximate by another velocity distribution. We assume, which is not true, that the velocity distribution is uniform. So we said that the velocity at the wall is uh, having an average value, right? Velocity here and here at the wall having a same velocity, and that velocity will be average velocity. So we assume in physical meaning that the fluid slip from the wire, as if it flew over an ice, right? When there is no friction, so the slip. But the mass flow rate remain the same. So this one equal to the rho V average time by d power of 2 divided by 4, right? So where d is the diameter, or if you don't want to write that, you can write as r power of 2 to get the same amount of mass flow rate. Okay, so when we want to define the Reynolds number, we are using the value of average velocity. Right, that is the definition of Reynolds number. Reynolds number is defined by the density time average value divided by kinematic dynamic viscosity time characteristic length.